the universe at its smallest. What we know about matter: the ancient Greeks surmised that the stuff of the universe was made up of tiny, uncuttable ingredients that they called atoms. Just as the enormous number of words in an alphabetic language is built up from the wealth of combinations of a small number of letters, they guessed that the vast range of material objects might also result from combinations of a small number of distinct, elementary building blocks. It was a prescient guess. More than 2,000 years later we still believe it to be true, although the identity of the most fundamental units has gone through numerous revisions. In the 19th century, scientists showed that many familiar substances such as oxygen and carbon had a smallest recognizable constituent. Following in the tradition laid down by the Greeks, they called them atoms. The name stuck, but history has shown it to be a misnomer, since atoms surely are cuttable. By the early 1930s, the collective works of J. Thomson, Ernest Rutherford, Niels Bohr, and James Chadwick had established the solar system-like atomic model with which most of us are familiar. Far from being the most elementary material constituent, atoms consist of a nucleus, containing protons and neutrons, that is surrounded by a swarm of orbiting electrons. For a while many physicists thought that protons, neutrons, and electrons were the Greeks' atoms. But in 1968 experimenters at the Stanford Linear Accelerator Center, making use of the increased capacity of technology to probe the microscopic depths of matter, found that protons and neutrons are not fundamental either. Instead, they showed that each consists of three smaller particles, called quarks, a whimsical name taken from a passage in James Joyce's Finnegan's Wake by the theoretical physicist Murray Gell-Mann, who previously had surmised their existence. The experimenters confirmed that quarks themselves come in two varieties, which were named, a bit less creatively, up and down. A proton consists of two up quarks and a down quark, a neutron consists of two down quarks and an up quark. Everything you see in the terrestrial world and the heavens above appears to be made from combinations of electrons, up quarks, and down quarks. No experimental evidence indicates that any of these three particles is built up from something smaller. But a great deal of evidence indicates that the universe itself has additional particulate ingredients. In the mid-1950s, Frederick Reyners and Clyde Cohen found conclusive experimental evidence for a fourth kind of fundamental particle called a neutrino, a particle whose existence was predicted in the early 1930s by Wolfgang Pauli. Neutrinos proved very difficult to find because they are ghostly particles that only rarely interact with other matter. An average energy neutrino can easily pass right through many trillion miles of lead without the slightest effect on its motion. This should give you significant relief, because right now as you read this, billions of neutrinos ejected into space by the sun are passing through your body and the Earth as well, as part of their lonely journey through the cosmos. In the late 1930s, another particle called a muon, identical to an electron except that a muon is about 200 times heavier, was discovered by physicists studying cosmic rays, showers of particles that bombard Earth from outer space. Because there was nothing in the cosmic order, no unsolved puzzle, no tailor-made niche, that necessitated the muon's existence, the Nobel Prize-winning particle physicist Isidore Isaac Rabi greeted the discovery of the muon with a less than enthusiastic, "Who ordered that?" Nevertheless, there it was. And more was to follow. Using ever more powerful technology, physicists have continued to slam bits of matter together with ever-increasing energy, momentarily recreating conditions unseen since the Big Bang. In the debris they have searched for new fundamental ingredients to add to the growing list of particles. Here is what they have found: for more quarks, charm, strange, bottom, and top, and another even heavier cousin of the electron, called a tau, as well as two other particles with properties similar to the neutrino, called the muon neutrino and tau neutrino to distinguish them from the original neutrino, now called the electron neutrino. These particles are produced through high-energy collisions and exist only ephemerally. They are not constituents of anything we typically encounter. But even this is not quite the end of the story. Each of these particles has an antiparticle partner, a particle of identical mass but opposite in certain other respects such as its electric charge, as well as its charges with respect to other forces discussed below. For instance, the antiparticle of an electron is called a positron. It has exactly the same mass as an electron, but its electric charge is +1 whereas the electric charge of the electron is -1. When in contact, matter and antimatter can annihilate one another to produce pure energy. That's why there is extremely little naturally occurring antimatter in the world around us. Physicists have recognized a pattern among these particles, displayed in Table 1.1. The matter particles neatly fall into three groups, which are often called families. Each family contains two of the quarks, an electron or one of its cousins, and one of the neutrino species. The corresponding particle types across the three families have identical properties except for their mass, which grows larger in each successive family. The upshot is that physicists have now probed the structure of matter to scales of about a billionth of a meter, and shown that everything encountered to date, whether it occurs naturally or is produced artificially with giant atom smashers, consists of some combination of particles from these three families and their antimatter partners. A glance at Table 1.1 will no doubt leave you with an even stronger sense of Ruby's bewilderment at the discovery of the muon. The arrangement into families at least gives some semblance of order, but innumerable whys leap to the fore. Why are there so many fundamental particles, especially when it seems that the great majority of things in the world around us need only electrons, up quarks, and down quarks? Why are there three families? Why not one family or four families or any other number? Why do the particles have a seemingly random spread of masses? Why, for instance, does the tau weigh about 3,520 times as much as an electron? Why does the top quark weigh about 40,200 times as much an up quark? These are such strange, seemingly random numbers. Did they occur by chance, by some divine choice, or is there a comprehensible scientific explanation for these fundamental features of our universe?